Hi everyone. In today's presentation, we will be covering chapter 2.5 in the OpenStax Prealgebra textbook, where we will cover prime factorization and the least common multiple. So our two learning objectives then are to find the prime factorization of a composite number and find the least common multiple, LCM, of two numbers. So let's first start then with the question, what is prime factorization? So prime factorization means rewriting a composite number as a product of prime numbers. So for example, let's say you have the number 36. This is a composite number because it has more than two factors. We can write 36 then as a product of its prime numbers, which would be 2, that's a prime number, times 2, that's another prime number, times 3, times 3. In other words, 2 times 2 is 4, 4 times 3 is 12, 12 times 3 is 36. So the prime factorization of 36 is 2 times 2 times 3 times 3, or if I put in exponential form, this would be 2 to the second power times 3 to the second power. Now, why does prime factorization matter? So prime factorization breaks a number into its smallest prime number pieces. You can basically think of prime numbers as the building blocks, the basic building blocks of all other numbers. And every single number has a unique prime factorization to it. So for example, if I started to do the first few composite numbers, let's say I had the number 4. 4 is a composite number that can break down into 2 times 2. The composite number 6 then can break down into 2 times 3. The composite number 8 can break down into 2 times 2 times 2, right? 2 times 2 is 4, 4 times 2 is 8. The composite number 9 can break down into 3 times 3. Each of these then are unique prime factorizations for that particular number here. Now, to complete prime factorization, there are two core methods we can use: the factor tree method and the ladder method. So let's first do a few questions that look at the factor tree method. And we're first going to start with the prime factorization of the number 52. So how we actually utilize this method is we start with the number 52 at the top of the tree, the proverbial tree here, right? Now, what we then do is we find any factor pair of the given number 52. So it could be composite factors or it could be prime factors. I actually like or recommend, as you first start this method, to start by going after the smallest prime number first. That gives you a nice little starting spot, and you can just work your way up from there. So if we start with the number 2, for example, we realize that 2 times 26 is equal to 52. So 2 goes into 52 because it's even. Now, what we can do here is I would circle the prime number, the number 2 here. And since this is a prime number, your branch is complete. And that's where the circling part comes in. That lets us know that we've completed the branch. Now, step 3 says if a factor is composite, we can break it into another factor pair. Now, so 26 is also even. So I like to then factor the number 2 here, again, the smallest of the prime numbers. That ends that branch. And 2 times 13 is 26. Now, 13 also is a prime number, right? The only two factors that go into 13 are 1 and 13. That's the definition of a prime number. So we can also circle the number 13 here. So writing out our prime factor list, we would say 2 times 2 times 13. Or if I shortened it down using exponential form, we would say 2 to the second power times the number 13 here. Now, usually proper orientation of prime factorization is to put the numbers in order and start from smallest to greatest here. Okay, so in either form, we are at the correct place. Let's try the number 68 now. So starting with the number 68 at the top of the tree here. This is even, so we can find any factor pair of the given number. I recommend just going ahead and starting with the number 2. We know that is prime, so 2 times 34 is 68. Now 34 is an even number, so that means it's still composite. So we could factor out another 2 here. So again, if a factor is prime, the branch is complete. If a factor is composite, break into another factor pair. We continue until each branch ends with a prime number, and then rewrite the composite number as the product of all the prime factors. Right? So 34 is composite, so I can continue breaking this down into 2 and 17. Now 2 is prime. What about 17? Well, again, 17 only has 2 factors, 1 and 17. There are no other number that divides into it. 2, 3, 4, 5. You can check all those numbers. None of those numbers actually breaks down 17. So we would also circle that number as well. Now, step 5, write the composite number as the product of its prime factors. So this would be 2 times 2 times 17 here. Now, again, I can write this as exponential form as well. 2 squared times 17 as another form of this answer. Now let's look at the number 96 here. So again, we can find any factor pair of the given number. Let's go ahead and start with the smallest of the prime numbers, which is the number 2. 2 again goes into 96 because it's even. So we can say 2 and 48 here. 2 can then be circled as our first factor pair. Now 48 is also even, so I can factor by another 2 here. So 2 and 24 go on to 48. So I can circle 2 here. 24 can continue to be factored down into 2 and 12. And then 12 can be factored down into 2 and 6. So again, if I'm starting with all the smallest prime numbers first, we have 2 and 6. And then finally 6 can be factored down into 2 and 3. Now, 3 is a prime number as well. So at this point, all the branches have now been covered and the prime number is circled. So if I was to write the composite number 96 as the product of all the prime factors, we would say 2 times 2 times 2 times 2 times 2, 5 2s, times the number 3. If I was to shorten this down, it would be 2 to the 5th power times a number 3. Okay, so we have now completed the prime factorization of 96 here. Next, let's go ahead and do prime factorization using the ladder method, so the second method, and we'll do this with the same numbers we did for the tree method and compare the two methods together, right? So first we'll find the prime factorization of 52. Our steps then are to divide the number by the smallest prime, continue dividing that prime by that prime until it no longer divides evenly, divide by the next prime until it no longer divides evenly, and continue until the quotient is prime. And then finally, like the tree method, we'll write the composite number as the product of all the primes on the sides and the top of the ladder here. So let's first start by dividing 2 into 52. Okay, so at the top of this, 2 goes into 52 26 times. Okay, so it goes in 26 times here. Next, we're going to again divide 2 into 26, and 2 goes into 26 13 times. Now 13 is a prime number, so we now have the quotient, basically that's the 13 here, continue until the quotient is prime. The quotient is now prime. So we're now going to look at the sides of the ladder. This is 2 and 2, and the quotient of the ladder, that's 13, and we can write as a product of all the primes. So 2 times 2 times 13, and we get 52. Again, you can write this in exponential form as well. 2 squared times 13. Okay, let's try the next number. So the next number is to find the prime factorization of 68 here. So I'm going to, again, divide. Basically looks like our ladder here. Divide 2 into 68. Well, 2 goes into 68 34 times. We're going to try 2 into 34 again, which it does go in. 2 goes into 34 17 times. So again, 17 is a prime number, so our quotient, continue until the quotient is prime. The quotient is now prime. So we're going to write the composite number as the product of all the primes on the side, that's 2 and 2, and at the top of the ladder, that is 17. So it is now 2 times 2 times 17, or 2 squared times 17, and the other manner here. The last number we'll look at then is the number 96. So again, we'll try 2 into 96 to start. So 2 goes into 96 48 times here. So again, we're going to try the next part. 2 into 48 here. 2 goes into 48 24 times. So we're going to try another 2. 2 goes into 24 then. Let me put a little hook there. 2 goes into 24 12 times. Try 2 again. 2 does go into 12. Goes in 6 times. Now 2 into 6. 2 goes into 6 3 times. And we finally have now matched up to our prime number quotient. So we have the sides of the ladder, 2 times 2 times 2 times 2 times 2. That's 5 2's times our 3. Times 3, or 2 to the 5th power times 3 as our result. Apologies for the terrible drawing of the ladder. Luckily, I don't teach art, so there we go. Let's go ahead and continue on now to the next concept, which is the least common multiple. So what is the least common multiple, or LCM? The least common multiple is the smallest number that is a multiple of 2 or more numbers here. So for example, let's say we're trying to compare the number 4 and the number 6 here. So the number 4, if I was to first look at the multiples of 4, we have things like 4, 8, 12, 16, 20, and 24. Let's go ahead and stop there for now. Obviously, multiples continue going on. And then the multiples of 6 include 6, 12, 18, and 24 here. Now, the common multiples, if I was to define the common multiples that I see, we have the number 12 and 12, and the number 24 and 24. Now, the least common multiple is the smallest of these. So the smallest of these common multiples is the number 12. So we would say the LCM, or least common multiple, of 4 and 6 here is equal to the number 12 here. Okay. Okay, so let's go ahead and continue to find the least common multiple. The first strategy we will use to solve this is using the listing method. So let's start with the numbers 8 and 12. So with the listing method, step number 1 is to list the first several multiples of each number. Step 2, look for multiples common to both lists. If there are no common multiples in the lists yet, continue to write out additional multiples for each number. Then look for the smallest number that is common to both lists. This number is the LCM. Okay, so starting with the number 8, and then we have 12 here. So if we start with the first few multiples, let's say we start with the first 3, so 8, 16, and 24. And then we write out with 12, we have 12, 24, and 36. So starting with the first 3 multiples. In this case, we do actually see a common multiple here, right? We see the multiple 24 and 24. That's the least common multiple. Now, these numbers do share some other multiples, right? So if I was to list out the first 5 of these, or first 6, I should say, really, 32, 40, and 48, and then I continued with the number 12. The number 12 after 36 is 48. 48, not 20. We see these match up too. But since these are common multiples, but they're not the smallest, so they would not be considered the least common multiple here. Another number we can look at is 6 and 9, 2 numbers. And we can compare the list. So again, following the same steps we are doing for the listing method, we can have 6 and 9 here. So if I started with the first 3 numbers for 6, we have 6, 12, and 18. And for the number 9, we have 9, 18, and 27. Again, this isn't always the case, but we have the number 18 that does appear in both lists. That is the least common multiple. If I went further just to kind of show other multiples, we have 24, we have 30, the number 30, and then 36. And then 9, we have 36, and we have 45. We see that the number 36 does match up in both lists as well. But the least common multiple, again, the LCM, would be the number 18. Let's now try 14 and 21 here. So if I look at some multiples of 14, we have 14, 21, not 14, 21, 14, 28, I should say, 42, 56, 70. Let's go ahead and go out that far. 21 then, we have 21, 42, 63, and 84. Which if I actually went out one more for 14, I would also get to 84. Some of the common multiples that I see here is then the number 42 and 42. And we also have 84 and 84. So in this case, the LCM, the least common multiple of 14 and 21, is the number 42. So that is finding the least common multiple with the listing method. There is another method for finding the least common multiple, and this is using prime factors and prime factorization. So the examples I provided for the listing method, really the listing method probably is the easiest, it's the most straightforward, because the numbers are relatively small and you're really only comparing 2 of them. But if the numbers are larger or you have multiple LCMs to look at, then this method using prime factorization can be quite useful. So how do we use this method? Well, first, we're going to find the prime factorization of both numbers. And I'm going to go ahead and use the factor tree method to solve this, or to do the first step, find the prime factorization of each number. So we can take the number 8 here. Let's make this black. So 8 and 12 here. So then 8 can be factored down into 2 and 4. So 2 is a prime number again, and 4 can be factored down into 2 and 2 here. Okay, so now we have all of our prime factors here. 12 then can be factored down into 2 and 6, and 6 can be factored down into 2 and 3. All right, so now we have our prime factors list, prime factorization list, I should say. Step 2, write each number as a product of primes, matching primes vertically when possible. So 8, we have 2 times 2 times 2. And 12, we have 2 times 2 times 3. So there's actually a missing number, or this 2 doesn't match up with this piece, and 3 doesn't match up here. So then what we're going to do is we're basically combining similar factors here that we can. So 2 and 2 can be combined. So we would bring that down, down the prime in each column. So 2 gets brought down here, times 2 gets brought down here, times, since we're looking at the least common multiple, not the greatest common factor, we then bring down the 2 here, and we bring down the 3 here. So essentially what you've done is you combined 2 of the 2's, really. So at this point now we have 2 times 2 times 3, or 2 times 2 times 2 times 3. Okay, so step 4, multiply the factors to get the LCM. So 2 times 2 is 4, 4 times 2 is 8, 8 times 3 is equal to 24. So the least common multiple, of 8 and 12 is equal to 24 here. Okay. Let's try with the next two numbers that was similar to the factor list. So now we have 6 and 9 here. Step 1, find the prime factorization of each number. So the prime factorization for 6 is 2 times 3. Now both of these are prime, so I can circle them. And then 9 is 3 times 3. Again, I can circle these. So 6 then, 2 times 3. Put an equal sign there too as well. I put an arrow in this case. 9 then is 3 times 3. Okay, so we've now wrote each number as a product of primes, matching primes vertically when possible. Step 3, bring down the prime in each column. So bring down the number 2 times, bring down a number 3 times, and then the other 3 that's not matched. So our least common multiple now is 2 times 3, which is 6, and 6 times 3, which is 18. So the least common multiple for 6 and 9 is the number 18 here. Looking at the last two numbers then, we have 14 and 21. So step 1, find the prime factorization of each number. So the prime factorization of 14 is 2 times 7. These are both prime numbers. And then the prime factorization of 21 is 3 times 7. Again, these are both prime numbers. Then we can write each number as a product of its primes. So 14, we'll go ahead and do equals in this case. So 14 is 2 times 7. Let me actually open this up because we're going to have a 3 that goes in its place. So then we have 21, which is equal to 3 times 7. So then we can match up our columns here, or bring down the prime in each column, I should say. So bringing down the number 2 times the number 3 times the number 7. So 2 times 3 is 6. 6 times 7 is 42. So the least common multiple of 14 and 21 is the number 42 here. And we're finished. So to recap, we have two methods for solving the least common multiple. The first method is the listing method. In this case, you list the multiples until you find the smallest common multiple. And this is a great method for smaller numbers. And basically, in the examples I provided, they're small, and the questions that are found in the textbook for OpenStax, relatively small numbers. The next method is a more versatile method. It gives you a much better understanding of numbers as well. So it is a method I'd spend some time working on and mastering. And in this case, you're using the prime factorization of the numbers to build your least common multiple. Remember, prime factorization and the prime numbers are basic building blocks of all numbers, which is why you can use it to help you define the least common multiple. This is much better than for our larger numbers. Okay, so in this presentation, we have covered both the prime factorization. We've looked at prime factorization using the tree method and the ladder method. I'd spend some time looking at both, and then you can choose which method you prefer. And then we've looked at finding the least common multiple using both listing and prime factors. So I'd go ahead and take a look at the OpenStax textbook now. If you have any questions, feel free to reach out. Otherwise, good luck. Thanks, everyone.